in single variable calculus, when it comes time to determine whether a critical point is a local maximum, a local minimum, or neither, you had a couple different options. One of them was called the first derivative test, where you use the first derivative because it tells you where a function is increasing and where it's decreasing, to say, well, what is my function doing on the left side of my point? What is it doing on the right side of my point? Because if that point is where a function is changing from increasing to decreasing, then that must mean that we had a local maximum. If the function is changing from decreasing to increasing, we must have had a local minimum. And if it's not changing at all, then we must have something called an inflection point, right? Where it might be increasing and then it levels off and then it starts increasing again, or decreasing. Excuse me. So again, in multivariable calculus for functions of several variables, we have to have something a little bit more sophisticated, because there's not just a one-dimensional directionality, right? Just like when we were talking about limits a couple weeks ago. Limits in single variable calculus only have two flavors. We can approach a point from the left or we can approach it from the right. But in multivariable calculus, we have this whole infinitude of different ways that we can approach a point. And that means that we kind of have an infinitude of different ways that we could pass through a critical point that we would need to investigate. Is it increasing and then decreasing this way? Is it increasing and then decreasing that way? And so on and so forth. So it's not quite as straightforward of a question. What we'd like to do, though, is see if we can adapt not the first derivative test from single variable calculus, but the second derivative test. Because the second derivative in single variable calculus was used to measure the concavity of a graph. If the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down. And we can use whether a function is concave up or concave down at one of its critical points to determine whether we had a local minimum or a local maximum. And so the second derivative test in single variable calculus, we use to say if our function is concave down at a critical point, then that critical point is a local maximum. If our function is concave up at a critical point, then that point must have been a local minimum. And so in this activity, we're going to try to build towards something that looks like a second derivative test for multivariable functions. The problem, of course, being that we have many different second derivatives that we can compute for a function of even two variables. It has three different second derivatives, actually in principle four. The x partial derivative, the second partial derivative with respect to x twice, the second partial derivative with respect to y twice, and then the two mixed partials, f sub xy and f sub yx. And so somehow we have to figure out how all of those different second derivatives can be smushed together to tell us something about the concavity in two dimensions of the graph that is a surface. Is it concave down in every direction? Is it concave up in every direction? Or are there some directions along which it's concave up and other directions along which it's concave down? To start walking the road towards a second derivative test for a function of two variables, in this activity we have three different functions to look at. There's this 4 minus x squared minus y squared, which has a graph that looks like this. There's f of xy equals x squared plus y squared, has a graph that looks like this. And f of xy equals x squared minus y squared, which has a graph that looks like this. And so as you might expect, right, the function whose graph is shown at the left here is going to be our prototype for what a local maximum looks like, right? Because we have sort of this top of the mountain. There's a xy where the value of the function at this point is greater than the value at any point that surrounds it. Our x squared plus y squared function, the one in the middle, is going to be our prototype for a local minimum. Right? There's an xy whose z value is smaller than all the z values that surround it. And then the one of these has a graph that looks like a saddle, right, where there is one direction along which it looks like my graph is concave up. So if I look along the x direction, this graph looks like it's concave up. But then there's another direction, the yz direction, along which it looks like my graph is concave down. Right? And so just like the saddle on the back of a horse, which goes downward on each side of the horse, but then has an upward bend that's sort of, between neck and hips, right? That we would call this a saddle point, or sometimes I call it a Pringle point, after the Pringles, the shape of a Pringles potato chip. It's like a perfect hyperbolic paraboloid. So the point of this is going to be to, first of all, do the find and classify or find critical points process for each of these three functions. It's not going to take us too long to do. And then take a look at how the second derivatives are going to tell the difference between these three different scenarios. So that's the purpose of this activity. So part A, just find the critical points and use the graphs to say which one of these should we call a local maximum, which one should we call a local minimum, which one should we call a saddle. And I think I've already given that away in my opening remarks here. And so the interesting part starts in part B, where you have this combination of second partial derivatives, the product of the pure partials minus the square of the product of the mixed partials. And to calculate this quantity for each of the three cases and see if that quantity can tell apart the three different types of critical points that we see, and if so, how. So in this problem, you took this quantity, which is the second x partial times the second y partial, minus the square of the mixed partial, so fxy squared, and computed that number. The authors of this book call it capital D. I call it capital Greek letter delta, and the notes typically when I take them. I call this the discriminant of this particular quadratic. And what you're saying here is that when that quantity is positive, then we have a local extremum, either a local minimum or a local maximum. When that quantity is negative, then we know that we have to have a saddle point, or at least we don't have a local maximum or a local minimum if that quantity is negative. So the way that I like to think of it is that when that quantity is positive, it means that all of the concavities of my function are the same at that point, right? It's either all concave up or it's all concave down when this discriminant is positive. Whereas when this discriminant is negative, we know that there's going to be some concavities that are positive and other concavities that are negative. So as one example, right, let's suppose that the second partial with respect to x and the second partial with respect to y have opposite signs from one another, which is what happened in the x squared minus y squared case. Right? Then if that's true, then already we know that the concavity of the graph in one direction, in the x direction, is going to be the opposite of the concavity of the graph in the other direction, the y direction. And so automatically having those two pure partials have opposite signs should immediately guarantee that we do not have a local maximum or minimum at that point, because we have a discrepancy in the signs of the concavities. And so the interesting question is, why is it true that when this discriminant is positive, that we know that all the concavities agree at that point? And so I do want to talk a little bit more about that after we wrap this activity up. But in the end of this activity is going to ask us to do that second step decision, which is, suppose that I have a positive value for this discriminant. How do I determine whether that is telling me that I have a local minimum or whether it's telling me that I have a local maximum? So just knowing the discriminant is positive doesn't tell the difference between those two, so we need one more step in our decision process. We can classify local maximum versus local minimum. Once we know that the discriminant is positive at a critical point, we know that either that critical point is a local max or it's a local min. And so the way to figure out which it is, once we know that all the concavities are in the same direction, which is what a positive discriminant tells us, then we just have to test one concavity to figure out whether they're all up or all down, right? Because they're all going to follow the lead of whichever one that we check. And so if we check the concavity in just the x direction, and we find that fxx is negative, that means that in the x direction the graph is concave down. And having a positive discriminant tells me that therefore all of the concavities in any direction at that point are all concave down, so we must have a local maximum. Conversely, if the x direction concavity fxx is positive, that means that our graph is concave up in the x direction. And if, in addition, the discriminant is positive, that means that it's concave up in every direction, so we have a local minimum. And so your comment at the end here is correct, that because the discriminant being positive tells me that all the concavities are the same, it doesn't matter if I check the x concavity or the y concavity in this process, right? Either one of them by itself is going to tell me not just what the concavity is in that direction, but what the concavity is in every direction in the case where the discriminant is positive. The question is, what happens if the discriminant is equal to 0? What happens if d is equal to 0? And just like in single variable calculus, in the second derivative test, when the second derivative was 0, the single variable calculus second derivative test didn't tell us anything, right? Having a second derivative of 0 doesn't help us to classify a critical point as a local max or a local min, or neither. It could be anything in that case. And the same thing is true in multivariable calculus. When the discriminant is equal to 0, it means that the first and second derivatives combined don't have enough power to tell us whether or not that point is a max, a min, or a saddle. And so you might need to look for some more information. So that case is called a degenerate critical point, or a singular critical point, whereas the cases where the discriminant is non-zero, those are called regular critical points. And so regular critical points are the ones that the first and second derivative alone are sufficient to classify as max, min, or neither. So just as a recap to how this all works, we can classify a critical point of a function of two variables by looking at its discriminant. Discriminant is just the product of the pure partial derivatives minus the square of the mixed partial, fxx, fyy, minus the square of fxy. And if that quantity is non-zero, we call it a regular critical point. If it's equal to zero, we call it a singular critical point, and we just sort of wash our hands and walk away. And we might have to classify it in some other way, but we're not going to do any of those examples really, because we have not much time in our semester. And so taking that delta value, that discriminant, if it's positive, it means all the concavities agree at that critical point. So then we just need to test one of them. And if that one, for example, the x second partial derivative is positive, then that means we have a local minimum. If that x partial is negative, we have a local maximum. If the discriminant is negative, it means that there is not agreement between all the different concavities of the function at that point. There's some direction along which the function's graph is concave up, other directions along which it's concave down, and so we must have something that we would call a saddle point.